Okay, welcome to the course. The first thing that we always do when we start working with a new device is to see whether all the hardware and software are properly configured. Okay, and that will be tackling in this first exercise. So, what we'll be planning is we will be understanding in an abstract way how we can create a microbleeds based design and add a UART peripheral to it. Finally, we'll send some random string so that we able to observe whether hardware and software are properly configured. Okay, so let us start with a new project. So we'll click on create project. So this will open up a window which will allow us to configure various settings required for creating a project. Okay, so we'll just go ahead and we'll click next. Now once you click next, you'll be finding you get a wizard where you can specify the project name. Now you can stick to a default project name, which is a project underscore 104 in this case. You can also select the directory where you want to save your project. Okay, and you can also set this specific directory as a default directory. So next time when you create a new project, all the projects will be added into that directory. Okay, so once you create next, I'll be finding the various projects that have been shown on the screen. So first one we have is an RTL project, then we have a post synthesis project, IO planning project, imported project, and an example project. Okay, so to view the existing project supported by a Vivado or supplied by a Xilinx, we can select the last option, which is an example project. If you have an existing project, you can just select an imported project option to open and view the various things that you have in an existing project. If you are working with a IO planning project where you are specifically connecting the peripheral to the FPGA chip, then you can select IO planning project. Sometime you might be using a third-party software for generating the build file or a synthesis file, which are basically .ngc file. So in that scenario, when you are utilizing a third-party software to generate a synthesized file and you want to test that particular design onto an FPGA, then you can actually go ahead and select the post synthesis project option. But we do not have uh, either a project post synthesis project, IO planning project, or imported project, or in fact we also do not need to explore an example project. So we'll stick with an RTL project. Now RTL project give us an access for creating a new project. So we can add our block design where we can add a microblaze as our standard device and we can work around. Okay, so we'll just go ahead, select an RTL project, and then we'll click new. Right now we'll be finding the next option that we get is a window where we can add sources. Okay, now sources can be Verilog or a VHDL sources. In fact, we can also add a test bench sources. But when we are working with an embedded processor design or a design consisting of an embedded processor, there we usually do not create a Verilog or a VHDL sources. Instead, we try to utilize the Vivado IP integrator, and we like to work for most of the time with an IPs. Okay, if you specifically require to have an hardware accelerator, then in that scenario you can add sources, but that will be exploring later on. So we'll keep this option blank since we will be predominantly working with the block design for major part of the course. And when we actually discuss how we can build a custom XI interface, there we'll add a sources. Okay, so we'll just keep this blank and we'll proceed. After this, you'll be finding we get an option where we can select the part. Okay, so if you are working with a bare chip, then you can go to a parts. If you are working with a development board, then you go to a board tab and we'll choose a Nexus 4 DDR as our default development board for the course, right? Then we'll click next and finally we'll hit finish. Okay, so once you hit finish, it will basically create all the necessary folder inside the directory that you have specified with all the necessary file to get us start working with the environment, Vivado environment, and the device that we have selected, right? Now we'll notice that there are various windows that are provided inside a Vivado to help us get started with both the normal Verilog flow as well as an embedded system design flow, right? So on the left side, you'll be finding all the options that are required to perform an FPGA design. So we start with a project manager where we can change the device that we are currently utilizing. Along with this, we also can see an IP catalog where various IPs that have been provided by Xilinx are available, right? And somewhere if we stuck, we can go and refer to a language template. So these all options are very useful when we actually work with an Verilog or a VHDL sources. Second option which we will require is an IP integrator. So throughout the course, we will be majorly focusing on an IP integrator, which provide us a option to work on an IPs and the block design. Okay, so the connection and an entire canvas helps to accelerate the design of an embedded system. Below an IP integrator, you also have a simulation, right? So simulation, RTL analysis, synthesis, implementation, everything can be used for both either an pure RTL design or an embedded system based design. Okay, so we'll go ahead and we'll click on create a block design. Since we do not have an existing block design, so we'll create a new one, and there we will be adding our design. Okay, so here on a center you'll be finding the canvas where we can actually add an IP. If you just click on this plus sign, okay, and search for a microblaze, you'll be finding a microblaze IP has been automatically added. So this is always the first step that we do. Once we create a new block design, we go ahead and we add a microblaze. So that will always be the first step when we start working with an embedded system design with a microblaze. Okay, now this immediately won't give us all the functionality of a microblaze, so we need to configure it. So how we configure an IP is by clicking on run block automation. So this will add a necessary clocking and reset circuitry along with the local memory. So we'll change a local memory to a 64 KB, which will suffice most of the application need, and we'll just hit OK. So Vivado will automatically add a clocking, reset circuitry and the local memory utilizing a BRAM inside our block design, which is not that much big, but anyway we also have an access to an external DDR. So immediately we can store a huge data in a DDR, okay, utilizing certain protocols. Okay, now once we complete the process of block automation, you'll be noticing the reset and clocking circuitry has been added. But by default, the clocking wizard IP, if you observe, consists of an input which is differential ended. But for my board, or for a Nexus 4 DDR board, the clocking is actually a single ended clock. So to configure the clock source, we can just double click on the clocking wizard IP, and then we can actually choose the clocking source, right? So depending on the board that you are utilizing, you can choose either a single-ended clock source or a differential-ended clock source. So I'll just go into a clock in one and I'll select this clock. Now Vivado is an hardware dependent software. Okay, so as soon as you add a certain board, certain parameters have been set by default. So for example, you'll be noticing that clock in one, we have an option to directly select a sys clock. So it automatically identify the clocking related pin, and then other thing that we need to do always is to take the reset to be active low. Okay, so this is the second mandatory step that you will always be performing. And once we do this, we can go ahead and perform a connection automation. So this will automatically connect a clocking wizard IP to the clocking and the reset sources that we have on a board. Okay, so we'll just go ahead and we'll hit on run connection automation. We'll select entire thing since we want to connect clocking option as well as a reset option. So we'll just select an entire thing and we'll just hit OK. Now we'll be finding the reset will be automatically added and the system clock is automatically added. One more thing that you can do is you can go to a board tab and verify that whether system clock and reset actually belongs to board clock and the reset type. So you'll be finding the system clock is having a check mark which indicate that we have connected clocking wizard IP to a correct source. And second verification check will be to verify whether reset is also been connected to the board reset, and you will be finding a board have a reset pin and just neighboring to a reset we have a check mark. So both system clock as well as reset has been connected to their dedicated sources, right? So this completes the mandatory source. Now we have a reset and clocking circuitry added to a clocking wizard IP, microblaze with a local memory. Now we can just regenerate layout, okay, to see a cleaner diagram on a canvas. Now we'll go ahead, since we want to utilize UART, okay, so we'll just go ahead and select an UART light IP. Later on we'll understand what UART 16550 is. So once we have our IP placed on a canvas, the first thing that we always do is to configure the necessary settings. So we'll just double click on an IP and then we'll choose the default configuration setting, that is what should be the baud rate and then where it should be connected. So we'll choose the baud rate to be 9600. Now we will handle an entire process of connection to a Vivado by clicking on run connection automation, right? So this will take a while to perform the connection between the microblaze and an IP. We'll just select everything and we'll hit OK. Now we'll again regenerate layout so that we have a cleaner diagram of an entire block design. Okay, so this completes an entire scenario. So we have our microblaze that has been connected to a UART light through an AXI interconnect. Okay, so AXI interconnect is a standard way of connecting a peripheral to a microblaze. We also have a local memory, clocking and reset. As soon as you complete your block design, the first step that we always perform is to validate design. So this will check whether all the mandatory connections are made or not. Okay, so once we have a validation successful, we can go ahead and we can generate a source code for it. So if I just delete the clocking line of a design, you'll be finding the design is actually failing, right? So validation of a design, check whether all the mandatory connections are made inside the design or not. So this is an important step that we always do. Okay, so I'll again correct an error by performing a connection automation and then I'll again perform validation of design. So once validation is successful, I'll create an source code. Since an entire Vivado software will require finally a VHDL or Verilog source, so we'll just right click on our design and we'll create an HDL wrapper. So now this will take a while to generate an HDL wrapper, and once our HDL wrapper is ready, you'll be finding it is automatically set as a top model, since all the process that we have on a left side, that is inside a flow navigator, are performed on a design which is a top model. Okay, so that can be easily identified analyzing a 3-chip on a VHDL or a Verilog code. So you'll be observing that we have a 3 chips on our design one wrapper, so it has been set as an top model. Okay, so now we can proceed with generation of a bit stream. Now since we have utilized all the peripheral which have been identified by default with an Vivado, so we do not need to add a constraint. Okay, once we add our own peripheral IPs, there we need to add a ports. So in that case, we need to perform an intermediate step, that is we perform synthesis, implementation and so on and so forth, right? Before actually performing generation of a bit stream, one more mandatory step that you can do is to check whether all the peripherals have been connected to their desired pins. Okay, so just go to a board tab and see whether all the peripherals have been connected to their desired port. So USB UART has been connected to its desired port, reset and clock has also been connected to the desired port. So once this verification is successful, we can go ahead and we can generate our bit stream, right? Okay, so our bitstream generation is successful. Now what we will do is we will go to file, we will select an export and export hardware. Since we want to export an hardware definition to an SDK, so we'll also include a bitstream. So what this means is we will be programming our FPGA from SDK itself. Okay, so there are two ways by which you can program your FPGA. One of the way is you can program FPGA from Vivado itself, and the second way that we have is programming an FPGA from SDK. Okay, so we'll prefer the second way until and unless we will be debugging the communication interface or intermediate wires. Okay, once you have a scenario where you need to debug the values of a net using an ILA probe, so in that scenario we prefer to program our FPGA from Vivado itself. When you are least interested in debugging your hardware design, we like to program our FPGA from an SDK, right? So then we will just go ahead again to a file, and then we have an option to launch an SDK. So we'll allow an Vivado to consider a default setting for exporting all the necessary file inside an SDK. Okay, so this will take a while to launch an SDK. Okay, so all the necessary files are been exported into an SDK. So you'll be finding all the IPs that we have added have certain base address. So this also indicate that the way by which we communicate with the peripheral is basically a memory mapped IOs, right? Now we go ahead to a file, new and application project. So here we'll choose a good name. So we'll go ahead with the top and we'll select an hello world template. So this give us preliminary drivers which are required to start working with an UART, and we'll just click finish. Okay, so this will add all the necessary drivers required to work with an UART. Now you'll be finding two folders are been added. One is in top folder and other one is in top underscore BSP. So we'll go to a top, and inside a top you'll be finding hello world.c file, which is our main file. Okay, so we'll just go inside that, and then you'll be finding a code is been provided for us. So we'll just delete out the comments. So three libraries have been included right now. First one is an stdio, then we have a platform.h, and then excel.print h. Okay, so these three drivers have been added with an hello world template. So init platform and a cleanup platform are the preliminary setting required to work with an UART. Okay, will not work with a print because it consumes a lot of memory if you compare it with an ZIL printf. So we'll just delete print. Okay, and we'll add ZIL, that is XIL underscore printf. So this will be our standard way to communicate with an UART interface. Okay, so inside this, inside the parenthesis, we will add a double quote and we'll add a message that we need to send to a console. Since we are utilizing this exercise to see that whether our hardware and software tool chain is correctly operational. Okay, so we'll just add microblaze tool chain is successfully configured, right? And then we'll just save our code, and once we save our code, at the top you'll be finding we have an option to program an FPGA. Click on that option. So this will generate all the necessary files and will start programming an FPGA. So once FPGA configuration is successful, we are ready to run our application on an FPGA. So once our FPGA configuration is successful, the first thing that we always do is to connect an SDK terminal. Okay, so we'll go to an SDK terminal, we'll click on plus sign, we'll select the correct port. So in my case it is COM15, and also the baud rate we have set in this exercise is 9600. So we'll select that and we'll just hit OK. Okay, so once you see the message connected to a COM port 15 at the specific baud rate, you can be sure that your console is working fine. Okay, now we'll select the top folder where we have our hello world.c. We'll right click, run as, and then launch on hardware debugger. Finding that inside the SDK terminal, we able to see the string that we have added inside and ZIL printf. So this suggests us that the entire tool chain is properly working, and we can go ahead and consider the complex scenario with a microblaze.